I know you're very interested in this topic because it's joint work with you. And thank the organizers for inviting me to this wonderful workshop. So the title of the talk is Removal Lemmas for Kneser Graphs and Product Graphs, or the Swiss cheese phenomenon, which I will describe shortly. And here's a table that gives some insight or background about what I'm going to talk about. It has 3 columns. The first 2 columns relate to graphs, and the third is a hypergraph. And the first column is where the theorems sound most interesting to combinatorists when they're stated. The second column is where we really work. When we think about this, it's where we try to do the proofs. And the third column is the one that gave us inspiration. So I'll explain. What are these 3 columns? The first column is the Kneser graph with parameters n and n over 3, but 1/3 is just an arbitrary choice. You can put there alpha n for any fixed alpha. The vertices of this graph are all subsets of n of size n over 3. So you take all subsets. These are the vertices. And 2 are connected by an edge, AB, if they're disjoint. Okay? So an independent set in this graph is a bunch of vertices. It's a bunch of sets which every 2 intersect. It's an intersecting family. So independent sets in this graph are intersecting families. And the degree in this graph, if you fix a set, how many disjoint sets do you have? It's 2/3 n choose n over 3, which is much smaller than n choose n over 3. So this is a sparse graph. Okay? And one remark, since we're going to use analysis and we do this based on product graphs, the way we actually deduce theorems about this, it's very similar to a graph. You take the 2-point graph with a loop on 0, and you endow it with a measure 2/3 on 0 and 1/3 on 1, and then you take its tensor with itself n times. So that gives you a Kneser graph on all subsets of n, but the measure is concentrated near the sets of size n over 3. And you can, by analyzing what happens on this product graph, you can deduce a lot of things that happen in this on one layer. Okay. So you put a measure. I'm going to talk throughout the talk about sizes of sets, but you can put weights on the vertices and then study the measure of sets. A small set or a large set won't mean number of vertices, but its measure. So if you just put the measure 2/3 on 0 and 1/3 on 1, and then you take the product measure. So the measure of a vector is 1/3 raised to the number of 1s times 2/3 raised to the number of 0s. And then that measure is concentrated near the vectors that have approximately 1/3 n over 3 1s. So
what is the product graph here?
So the product is that, let's look at this. It will make it easier to explain the product. Whatever the product is, I'll tell you in a second, it gives you the Kneser graph. It means that for 2 sets to be neighbors in the graph, they have to be disjoint. Okay? But the product is that in every coordinate, you have to be a neighbor in the base graph. So the second graph is you take the triangle and raise it to the nth power. So if the vertices of the triangle are 0, 1, 2. Oops, I'm missing an n here. So the vertices of the big graph are all trinary strings of length n. You take a string of length n of 0, 1, 2. So you have 3 to the n vertices. And 2 vertices are connected by an edge if they differ in every coordinate, which means in the base graph they're neighbors. 0 is the neighbor of 1 and 2, but not of itself. So 2 vertices are neighbors. This is very different from the Hamming graph. It's the opposite of the Hamming graph. 2 vertices are neighbors if they differ in every coordinate. So what's an independent set here? It's a bunch of vertices such that every 2 of them agree on some coordinate. And the canonical example is just fix all vectors whose 17th coordinate is 2, or whose 30th coordinate is 0. So those all agree on some coordinate. Hence, they don't span any edges. That's an independent set. And here the degree, well, if you fix the vector and you have to change every coordinate, you have 2 choices for every coordinate. The degree is 2 to the n, which is little over 3 to the n. So this is also a sparse graph. The third column is a hypergraph. Its vertices are the edges of the complete graph. Fix n points and look at the pairs. These are the vertices of the hypergraph. And the edges of the hypergraph are triangles. Take any three pairs which form a triangle, A, B, B, C, A, C. So the number of vertices is order of n squared, but if you fix 2 points, they only belong to n minus 2 triangles. So here, too, it's a very sparse hypergraph. The degree is only n minus 2, whereas it could potentially have been order of n squared. So all these three creatures are very sparse. Now let's talk about, in all these cases, it's easy to describe the maximal independent sets, but there's also a stability phenomenon. So I'll explain what that is. Let's start from this column. A maximal triangle-free graph. This is Montel's theorem from 1907, not 2007, which it's just a special case of Turin's theorem, which was proved more than 20 years later. If you have a graph with no triangles, it has at most n squared over 4 edges, or n over 2 ceiling times n over 2 floor edges. So that describes what the maximal triangle-free graphs are, or how many vertices you can take in this hypergraph without spanning an edge. But there are a lot of stability results, and I couldn't even cite all the different proofs that if you have a graph which is triangle-free and has almost n squared over 4 edges, it means that it's very close to being bipartite. You can make it bipartite by very small changes. In this graph, the maximal independent sets are what I described before. Fix a coordinate and take all vectors that have that coordinate equal to your choice. That's 1/3. You have independent sets of size 1/3. And once again, there's a paper from 2004, Alon, Dinu, Friedgut, Sudakov, where we prove stability. If you have an independent set of size 1/3 minus epsilon, then it has to be close in structure to a real maximal set. The only way, a maximal independent set. The only way you can get a really big, close to a maximal independent set is taking a maximal independent set and playing around with it a bit. And for intersecting families, so if you fix K and you want to take as many K sets, subsets of N, and get an intersecting family, if K is less than N over 2, then the Erdős-Corrado theorem says the best you can do is fix one point, take all subsets that contain it. And here too there's stability. I should write here Hilton Milner also, but these are stronger quantitatively. So a paper of mine from 2008 using Fourier analysis and a paper of Kivash and Mubai from 2010 show once again stability. If you have an intersecting family whose size is close to n minus 1, choose k minus 1. But here, definition of close matters. Then it's close in structure to being an intersecting family. To being a maximal intersecting family. Okay, now, so if you look, for example, at this graph, we understand a maximal independent set. What about, is there any hope of describing all independent sets? Well, one thing you can do is take, so let's call the maximal independent sets the dictators, because you fix a coordinate and fix the value on that coordinate. Well, one thing you could do is take a subset of a dictator, of course. That's one thing you could do. But another thing you could do is, instead of a dictator, take a junta. So take all vectors who, on the first 3 coordinates, have at least 2 zeros. Okay, so that's junta because it depends only on 3 coordinates. That's not contained in a dictator, but any 2 such vectors share some coordinate in which there's 0, right? If you have 2 out of 3 zeros and 2 out of 3 zeros, they have to intersect. So you can get independent sets here by taking juntas. And it turns out, a paper of Dinu, Friedgut, and Regev from 2008, that essentially that's the only thing you can do. You take a junta that gives you an independent set, then you essentially, but I'll describe this in greater detail in a second, then you can take a subset of the junta, a subset of an independent set is still an independent set, and then you can add a tiny little bit of noise. Add a few vertices outside and remove their neighbors. That's essentially the only thing you can do. And this is true also in the Kneser graph. If you have an intersecting family, it's essentially contained in an intersecting family which is determined by a small number of elements. This is a paper of Dinu and myself, where for some range of parameters it follows immediately from DFR, and for smaller, it's for any Kneser graph, even when the size of the sets is fixed or a little over n. But for fixed size, it follows from DFR. Now, here, describing independent sets is understanding all triangle-free graphs. So, Erdős, Kleitman, and Rothschild proved that almost all triangle-free graphs are bipartite. But I think if you use the semi-ready regularity lemma, I'm not going to say anything about it now, then you can really understand all triangle-free graphs. You take a semi-ready partition and the super partition is triangle-free, and that's, so your graph was close to something like that. So that really explains all triangle-free graphs. Now,
I must object. We really don't understand triangle.
No, well, it depends in what way you're counting. If you're interested, in dense graphs, then almost all the way to get the triangle-free graph is to take a fixed triangle-free graph and just blow this up, add whatever you want between this, and add epsilon n squared edges. That's the only thing you can do. So in spirit, it's similar to what I described before. I agree that if you want to understand sparse triangle-free graphs, then that's a whole different game. That's definitely different. Okay, now we're coming to today's talk. We're talking about removal lemmas. So this is our starting point. I said that this column gives us the inspiration. So the celebrated Rouge's semi-ready theorem from 1978. It's a triangle removal lemma for graphs. So here's what it says. For every epsilon, you have a delta such that if your graph spans less than delta n cubed triangles, so if you take a bunch of edges, it's, just a subgraph of the complete graph, and that graph has very few triangles, it means that you can remove very few edges and get a triangle-free graph. Okay? Now, I mean, the first 100 times I looked at this statement, I had to look at it at a long time to understand whether it's trivial or not. And eventually I decided that it isn't. So the easiest way to convince you that it isn't trivial is that it implies Roth's theorem. Okay? So it implies that any dense subset of the integers has a three-term arithmetic progression.
Easily.
But it easily implies, but that's a meta-argument. But here, okay, and I'll try to convince you in a second that it's an interesting statement. And so the dependence that Rouge and semi-ready got between delta and epsilon was that a tower of height 1 over epsilon to the fifth. And so a horrible dependence, and it's very, very, very far from the lower bound, which comes from Barron's construction. And for many, many years, it was considered a major open problem to improve this dependence. And 2011, Fox improved this dramatically from a tower of size polyepsilon to a tower of size log 1 over epsilon. And our proof essentially was inspired by Fox's proof. And I'll explain about that a bit more in a second. And it's amazing because this proof is really, it's quite accessible. It's something you can teach in a graduate class. It will take an hour to present the proof. It's really, really nice and you can understand. But it was considered a big deal. It appeared in the Annals of Mathematics, and it's one of those proofs that it may be hard to find, but in retrospect, so how come we didn't think of it before?
It would be nice to improve the T, right?
No, yeah, it would be nice to.
No, the gap is still huge.
The gap is still huge. Okay, now what are the removal? So this says if you have few edges in your hypergraph, you take a bunch of graph edges, which means a bunch of vertices in your hypergraph. If that bunch of vertices spans few edges in the hypergraph, it means that you can remove a small number of vertices and remain with an independent set in your hypergraph. And what we prove is one level down. The same thing in graphs. For this graph and many other product graphs, I'm not going to classify them for you now. The following holds. For every epsilon, there exists a delta. If you take a subset of the vertices that spans a sparse graph with compared to the host graph, which was sparse to begin with. So it spans only delta proportion of the edges in your host graph. Then you can remove a small number of vertices, compare a small percentage of the number of vertices in the host graph, and remain with a truly independent set. Now, why do I call this the Swiss cheese phenomenon? You have your graph is like a hunk of Swiss cheese. It's full of holes. In this hypergraph, you have many bunches of edges which span no triangles. In these graphs, you have many bunches of vertices. I mean, a constant proportion of vertices that span no edges. You have these huge independent sets. And now I challenge you. I say, can you take a hunk of this cheese? That suggested before the talk, I called it an induced sub-cheese. So you have to take a bunch of cheese, which is where the density is very low, which is very sparse. The only way to do that is just to take a hole and take a little bit of extra cheese. So if you give me a bunch of cheese that spans very little cheese, I know what you've done. I just removed some of the cheese and you just took one of those bubbles. And that's the same thing in these graphs. The only way to get a sparse graph is to take a large independent set and add a little bit to it. And the reason this is so delicate, if I add here a little bit of edges in a really small number of edges in these independent sets. So take these graphs and add a random matching, which would increase the degree from 2 to the n to 2 to the n plus 1. Then this would already be totally false, because what was before an independent set would now span, so I have an independent set which is 1/3 of the vertices. It spans very few edges, only those that happen to fall in from the random matching. So it would be order of n edges, really few edges. But if I want to make it independent, I'd have to remove one vertex from each edge in the matching. So this property is very sensitive. If you change the graph even slightly, it goes away. Which is one indication, for example, that trying to prove these things by algebraic or spectral techniques may be hard up to impossible, because adding a matching hardly changes the spectrum of the graph. You really don't see it in the spectrum of the graph, but it changes this property completely. Okay, so what time did I start or did?
We still have 42 minutes.
42 minutes, okay. Good, so 33 minutes or 43 minutes?
I don't think there'll be any question. If there are questions, then let's make it.
Okay, I'll try to aim for 33. I'll pay you later, okay? So right. Now, I like this theorem a lot, but our main motivation to prove this theorem was to strengthen a theorem of ours. So let me state the DFR.
In trying to understand this theorem, looking at the contrapositive, what does that?
The contrapositive says that if you have to remove a lot of vertices to become an independent set, then you span a lot of edges. So any graph which is far from being triangle-free in edges contains a lot of triangles.
So if you have, in other words, if you have n squared triangles.
No, n squared triangles is nothing. If you have,
No, let's say you start with a graph.
so for example, if you have a graph where every edge is contained in a single triangle, so we have very few triangles, that graph must be sparse, because okay, so that's one of the nice applications of this. That's, for example, a nice step in the proof of Roth's theorem if you want to use this. That's one of the ways to. Anyhow, so let's go back to DFR and let me give you a statement. So we're back in this graph where the vertices are ternary vectors of length n, and two are adjacent if they differ in every coordinate. So the following holds. And okay, so for every delta, there exists some j, which is going to be the size of my junta, such that for every independent set I, there exists a set j such that the following holds. So first of all, j is a little j junta. So j is a bunch of vertices where the admittance test to this set depends only on j vertices. So j could be 1,000, and you give me a vector. I have a fixed window of 1,000 coordinates. I look at that window and I tell you whether your vector is in big J or not. Secondly, of course, well, we want to say that j captures I. So if you take I and remove j, then this is less than epsilon of the total number of vertices in the graph. I could write here 3 to the n, but I want to keep the generality. This theorem should apply also to this graph. Well, as I said, that this is trivial. Why is it trivial? You can take j to be everything. Everything depends on 0 coordinates, and everything contains anything. So this would be trivial. So I'd also like to say that j really explains why I is an independent set. I'd like to say that j itself is an independent set. So I'm writing j is an independent set. Well, when we proved this in 2008, we wished this was true, but this isn't what we proved. We proved that j is almost an independent set, meaning that j spans order of j is very sparse. Okay, so here's the picture. This is our whole graph. Here's the independent set I, and j almost captures I. Maybe there's some small part of I that j does not capture. And j almost explains why I is an independent set. J is almost independent itself. But all we could prove is that j is sparse. Now, this is annoying. And we wanted to get rid of this. We wanted to remove this. And we observed that you can remove this with a removal lemma. That's not why it's called a removal lemma, but removal lemma. If I had a removal lemma, then I could j is now sparse by removing a little more of j. But let's say part of what I'm removing could belong to I. Then I get a truly independent set, and I get rid of this. So if I have the removal lemma plus the weak version of DFR, like I can call my own theorems weak. Like I can tell anti-Semitic jokes, but I don't want other members of the audience to call this a weak theorem. So you take the weak theorem and the removal lemma, and together you get the strong version, which is what's written here. And so that was our motivation for the removal lemma.
I'm still not clear on what
So-
how much of it is the hypothesis and what's the conclusion?
Okay, so you have an independent set.
Was it done on purpose that there is no L in the removal lemma?
Yeah, the L was removed. It's a removal lemma. You have an independent. Where is Prasad? There. You have an independent set. I want to say the reason it's independent is it's essentially contained in a junta, and that junta is an independent set. That junta explains why. So if your family was an intersecting family, it's contained in all vectors where you have 2 out of 3 of the first coordinates which are 0. I want that to be the explanation. So I found we could find a junta which almost contains your family, and that junta almost explains why it's independent, because that junta spans very few edges. It was sparse. But I wanted to totally explain. I wanted that junta to be really independent. But now we know that if this junta spans very few edges, by the removal lemma it can be fixed. I can remove another little part of the junta. And now I have a truly...
And you only lost a tiny fraction of I by doing that.
Yeah, so I'm removing a tiny part of... Everything is measured with respect to the size of the graph. So everything when I say I'm only moving an epsilon proportion of the vertices, an epsilon proportion of the vertices of the whole graph. Yes?
So, but the new J's you get is not going to be a junta again.
Excuse me?
The,
No, it is, because if J depends on J coordinates, I'm going to apply this theorem in 0, 1, 2 to the J.
I see.
Okay? So what is a junta? A junta, if you take J coordinates, it basically breaks my space into 3 to the J parts, where these parts capture most of my graph. But now I look at that graph and I remove a small proportion of those parts. Okay? And since all parts are the same size, removing an epsilon proportion of those parts means removing an epsilon proportion. But that's an excellent question. That shows that you're following the thought.
I'm not following you.
No. No, everyone else buys my lies, and you caught me. I should have said that.
So just to make sure, so now we can read it up to this.
So now
Now it's correct.
Now it's correct. This is a theorem without the almost. And
And for all epsilon, you mean? Start with all.
no. This should be delta. There is no epsilon in the statement of the theorem. Okay.
Little j, how does it depend on delta? You don't care.
Exponential or something like that. Right? I think it's exponential.
It's strong for...
You get into don't you get into
No. Okay, let's say in the weekday far it depends exponentially. In the
Polynomial. I think it's even polynomial now.
even polynomial.
Dinu or Schenker.
Okay, Dinu and Shankar. But I'll say in a second we get a tower. And now an amusing thing is, so I want to explain how we prove the removal lemma. We use the weak DFR to prove the removal lemma. So it was not only the motivation for proving the removal lemma, it's also what we need to prove it. Now, few remarks.
It's not so weak.
Yeah, okay. It implies the strong, so it can't be. So some remarks. Let's see. So the first remark is something about related work. These triangle removal lemmas were proved also in. You can look in an algebraic setting. Take the group 0, 1 to the n, and then finite triangles being x, y, and z, such that x plus y equals z. And there, Ben Green proved the triangle removal lemma. And recently, Puya Hatami and Sakdeva and Tulsiani, they improved Green's tower from polynomial height to logarithmic height in a manner that's similar to how Fox improved the Ruzha-Semeridi bound.
So what are you talking
This is a side remark that there are triangle removal lemmas for groups in algebraic settings. Some other remarks. So about the techniques we used here. So I already said that algebraic seems to not work. It seems to me that it can't work because this property is so sensitive. You change the graph a little bit and the spectra doesn't change, but the spectrum doesn't change, but the property you're trying to prove changes dramatically. And the second thing, since it reminded us of the triangle removal lemma, we thought maybe regularity, but regularity seems not to work also. And the thing is that these graphs are supremely non-regularizable. So they're sparse, but there's a regularity theorem for sparse graphs also. But these graphs cannot be regularized. No matter how small a chunk you take, if you take two sets, there's always the Swiss cheese always leaves us big bubbles between those sets. So if you want two sets where the density is preserved on all the subsets, those sets have to be really exponentially small. So you can't regularize this graph. So regularity seems not to be so good. Third remark, I want to say something about the dependence between epsilon and delta. So in all our examples, we try to find the worst possible dependence. The dependence we found is polynomial. Whereas what we can prove is a tower of height log 1 over epsilon. So we have it's quite amusing to me, I think. We have a trivial proof, a really, really easy proof that gives a tower of height 1 over epsilon. And if we mimic Fox's technique, then we can get a height of log 1 over epsilon. But
you really don't mean epsilon delta. There is no epsilon.
here, in the removal lemma. Okay, so if you span delta edges, in all our examples, you have to remove delta to the 1 over 100 vertices, whereas we get a tower.
This also shows up in a strong DFR, but now I think let's focus on the removal lemma.
Now we're going to prove the removal lemma. And I want to say something about what Fox does. What?
In general, proof even for the weaker bound is use some ideas from the Fox.
Well, I'll show the proofs. I'll show two proofs. They should take 5 minutes each, so you can see how easy the first proof is. And so Fox's basic idea is this: you partition. So first you define some index. Define an index. You partition the graph. You look and see that the graph still has a lot of triangles. Then you shatter, which means that you refine the partition. So you need a good shattering lemma. Shattering lemma.
So in general structure, it's the same as in...
It's the same as the proof of the regularity, but yeah, and repeat. Now, there's something that Oded and I don't completely understand yet, plus one small trick that without using that small trick, we don't know how to get the... and the small trick is beginning with the maximal matching in our case, or in his case, beginning with a maximal disjoint set of triangles. So this small trick, which, I don't know, maybe that small trick was what was missing for 40 years. I'll show you the trick. It's really strange. It's really elementary, but somehow, without using that trick, we can't go from poly height to log height. And, okay. How much time do I have?
Depends who you're asking.
No, so I started at 9:07 or 9:00?
17.
17 minutes? Okay, so I said we need a good shattering lemma. So now I'm going to state so what I want to do in the remaining X minutes is show you the proof of the removal lemma. It's very easy. And as I say, you need a good engine. You need a good shattering lemma.
17 minutes is what's needed to present a 5-minute proof.
No, that's perfect. So in the first 90% of the time, I'll do the first half, and then. Okay, so what's our engine? That's what I said here. We need the weak DFR. So here's a slight modification of the original DFR, but it's implicit in the original paper. So instead of the original DFR, I'm going to give you a bipartite version of this, and instead of the hypothesis being that you start with an independent set, the hypothesis is going to be that you start with a sparse set. So here's the setting. You have two potatoes. I'll explain to you what potatoes are. I should call them falafel balls, but after collaborating many years with Wojta Rodel, I adopted Eastern European terminology. In East Europe, these are things that are called potatoes. And so, no, these are potatoes. So I have W and W prime, which are in 0, 1, 2 to the L. And what I have here is just W times 0, 1, 2 to the N minus L, and W prime times 0, 1, 2 to the N minus L. So I take L coordinates, I fix them, and then I look at all vectors that have those, that on the first L coordinates look like W and W prime. And this, of course, this is an independent set in my graph. Remember, any two vectors that share even one coordinate can't have an edge within. So these are independent sets. And let's assume, but that W differs from W prime in every coordinate. So you do have edges going between these two. And now we have here a set A and here a set B. And my assumptions are that the size of A and the size of B are at least epsilon over 4 on the size of the potato. And AB span few edges. And I don't want to even say what few is. They span very few edges. And okay, so here's A and here's B. And intuitively, our explanation is why they span few edges is maybe because in here I took all vectors whose 90th coordinate was 0, and here also I took all vectors whose 90th coordinate was 0, and that's why maybe they don't have any edges at all. So the conclusion is that there are some new coordinates out of these n minus L coordinates. There's a junta among these coordinates which explains what happens. So the conclusion is that there exists I and J. So this is I, this is J, and I and J almost capture A and B, so A minus I and B minus J are less than, let's say, even epsilon cubed, the size of a potato. And I want I and J not to be trivial, so both the size of I and the size of J are less than, so let's call this 1 and this 2, are less than a 1 minus epsilon over 4 of the size of the potato. So I and J aren't everything. I didn't say how many coordinates there are in I and J. We're not going to care because soon we're going to start taking towers. But they're not everything. That's important. But furthermore, not only are they not everything, one of them has to be substantially smaller than everything. So either the size of I or the size of J is less than 3/4 the size of a potato. Okay? That's my shattering lemma. So when I have this situation, I can cut this potato into smaller potatoes, and then I want to iterate. And now I said this is the engine. I should say what's the fuel inside the engine, which is also the fuel inside DFR. It's mu. So M and O are here, or they're at the workshop. Krzysztof here, so only Ryan is missing. This is Moshe, O'Donnell, Oleszkiewicz. Using the invariance principle, this is precisely one of the settings where it's very useful, where you can deduce that not all influences are small, or not all Fourier coefficients are small. So using mu, you can deduce that in such a setting, there's a small Fourier coefficient, which is large, which is precisely what you use to shatter. So this is the fuel inside the engine. Okay, so now let me show you the proof of the removal.
Fourier coefficient which is large?
It's indexed by few coordinates, and it's large in magnitude. Or if you prefer, a low Fourier coefficient, which is large. Okay, so let me start with the silly proof, the proof which will give us that delta, which gives us a tower of height 1 over epsilon. So I have a set.
What are we doing now?
I'm doing a removal lemma. I'm showing you that in our graph, if you have a set that spans few edges, I can remove few vertices and make it independent. So I start with the set, and I take some arbitrary partition into potatoes. And I classify the potatoes into 3 types. These are the light potatoes. Light. Which means that in each of these potatoes, our set captures, let's say at most, epsilon over 4 proportion of the potato. Okay, so we have, our set is, these potatoes are vertices, we have a sparse set. In these potatoes, we don't have very many vertices from our set. Forget the light potatoes. Now, I look at the remaining potatoes, and some of these potatoes have edges between them, but some of them don't have any edges going to the other heavy potatoes, and these are independent. Independent among the heavy potatoes. So I don't care if there's an edge going to here, because I'm going to throw away these. And remember that every potato itself is an independent set. And so eventually this is going to be my independent set. And now I have active potatoes. So here are my active potatoes. Active potatoes. Now the idea is very simple. What I want to do is I want to take these active potatoes. I look at the 2 of them. Now, my hypothesis was that I started with few edges, but I want to assume that I start with really very, 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 very few edges. So even after I've iterated this many times, even if all the edges were between these 2 potatoes, still that would be few enough edges to apply my engine. So since now I think those of you who are used to these proofs understand where the tower comes in, because I have to make sure that the few edges is few even after I partition so many times, and each time I partition, this decreases, the size decreases exponentially, so I'm going to get a tower number of steps I do. So let's look at an active potato, and so if it's active, I can find some potato, if it's not in the independent. Oh, and then I repeat this, and each time I chop up these potatoes into smaller potatoes, some of them become light, Some of them become independent, and some remain active. And I continue this till the proportion of vertices in active potatoes is, let's say, less than epsilon over 2. And then I throw away all the active potatoes, I throw away all the light potatoes, and I've thrown away very few vertices in my set. So I throw away all the active potatoes. I continue till I had very few of them. I throw away all the vertices in the light potatoes. And even if all potatoes were light, that would only be throwing away epsilon over 4. So I've thrown away a few vertices, and I remain with an independent set.
That's like a standard proof of weak regularity.
It's very,
You should have said something. You should have said why this ends.
What? I did. No. Okay, so no, there are two things here. I'll get to you in a second, okay? So first of all, this is a very standard technique. It's very simple. Two remarks. First of all, I didn't show you how I shatter this. You do need a good engine to shatter. But, and why? So why does this end? So when I take two of these, I cut them into smaller potatoes, and I use one. So when I cut them into smaller potatoes, here are the two potatoes I'm cutting. The I and j miss about at least an epsilon proportion of the big potato. And the proportion of the number of vertices from my set which sit outside I and j is epsilon cubed. So most of these sub potatoes are light. So in every step, the number of vertices in active potatoes has to decrease by, let's say, a multiplicative factor of 1 minus epsilon to the 8. So after 1 over epsilon steps, I have very few active potatoes, and I can stop. Okay? I use the fact that when I have few edges, I can partition such that I capture most of my set, but I and j are still missing part of the potato. So the parts that are here are going to be mostly light. So I can take some proportion of the potato and remove it and move it to here. So
this is the older DFR.
Yeah, this is a variant on the older DFR. Okay, so this is a really, really easy proof, and okay, so now.
But you still didn't say that this has to terminate because you.
No, I said because the number of vertices in active potatoes decreases. So after 1 over epsilon steps, the number of vertices in active potatoes is order of epsilon. So you throw away all the active potatoes, throw away all the vertices in light potatoes. You've only thrown order of epsilon vertices away, and you're left with an independent set.
The tower is because this step you.
Right. Yeah, so this is exponentially. This introduces new coordinates. So for every potato, I introduce a new bunch of coordinates. So the number of potatoes in the next step is exponential in the number of potatoes I had in this step. So the number of potatoes increases exponentially each step. And I had to make sure that delta is small even compared to these very, 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 very small. No, but
1 hour in a lecture or 1.5 hours.
It's standard. It's not standard.
no, yeah, it's standard. By the way, okay, I'll save the way for the question.
It's easier if you do it with the cheese slices instead of potato.
Right. Okay. So now.
You get in good shape.
No, falafel. So now, so that was the tower of 1 over epsilon, and now we're going to do the Foxy proof. So Foxy proof, and this will give us tower of order log 1 over epsilon. And now this, so if you think this was easy, here's such a easy idea, but if without.
It's even easier.
No, it's not easier, but I mean, how come it took 40 years to think of this idea? Well, the idea is now, the proof looks very similar, but the only difference is we start with a maximal. We have our set, and we start with maximal matching in the set. So I don't know if you like proofs by contradiction or not, but if your original set was you had to remove at least epsilon proportion of the vertices to become independent, then this is true also if you restrict your set to this maximal matching, because you have to remove one vertex from each edge in the maximal matching. So you know that the size of the matching has to be epsilon or 2 epsilon or something like that. So you begin with a maximal matching. And now I want to run the same algorithm as before. So I'm doing a slight modification. I define the light potatoes to be all those where the weight is less than epsilon over 4. But now I always want to work with a matching. So if I throw away some vertices, I also want to throw away their partners. So first I throw away all the vertices in light potatoes, but then those vertices each have partners, so I throw away the partners also. But then a potato may have become, that wasn't light before, may become light now. So I continue with this. So this seems like bad news at first, but if you think about it a bit, every light potato can only contribute twice its total weight. So this, even if you iterate this, the closure of this process only captures epsilon over 2 proportion of the vertices. So you throw away light potatoes and all the partners and you iterate. And okay. Now, as before, you have active potatoes and you have independent potatoes. But now I want to use this. So every active potato A looks for partner B. So you're an active potato, means that you have some edge leaving you, so maybe you have several edges, and you look for some potato which is connected to you, and hope that in applying, now I'm going to apply this too. So here's A, here's B. I apply this lemma, I find I and J, and either I or J is less than 3/4 of the potato. And I hope that in applying 2, I, which contains A, is of size less than 3/4 of the potato. Okay?
Summarize.
What?
Over time, try to summarize.
Okay. No, I started at 9:07. Now it's 9:56, so I have another minute. Okay. So if you find B, then you're happy. Okay. So if I found some B such that in the shattering the heavy parts decrease to 3/4, then I'm happy. And now you just note that unhappy form independent set. Because if I have 2 unhappy potatoes, if they were connected by an edge, they'd look at each other and one of them would become happy by that. So the happy potatoes form an independent set, and in a matching, every independent set contains the most half of the vertices. So at least half the potatoes are happy. Okay, so I have these happy potatoes, and then here we have to do what Fox did and define some potential function. It's the entropy of the. I look at the density of my set in the potato. I look at the average entropy, and now if you've done these regularity proofs, then you're used to this. You partition. If I go from such a situation to I'm cutting off, if all of this is light, then the entropy will drop substantially. The average entropy will drop substantially. So if I'm looking at the entropy of the density, and all parts have density 1 or 0, then the entropy is minimal. So every time you have a partition where a lot of the parts are almost empty, you increase the entropy substantially. So the idea is that you define some index, and every time you see a pair like this, you can increase the index substantially, and then that gives you a better bound on how many times you can. You can't iterate this forever. This is a lot like the proof of the regularity lemma. So that gives you a better bound on how many times you can repeat this procedure, and that gives you this log 1 over epsilon times that you can repeat it, and that's it.
I'm not sure how much sense this makes, but is there a way to quantify how far this Swiss cheese phenomenon can go? So you said, you had the remark that these graphs are really not good regularization material. So I'm not even sure exactly what I'm asking, but how extreme can this phenomenon happen? What you described with this, what you call the Swiss cheese phenomenon. Am I making sense?
You mean how sparse?
Not to me.
How sparse can?
Drop it, and I'll ask you.
Okay.
So the missing idea for 40 years is this happy potatoes idea?
No, the idea was that if you start with a matching, the key here is that when you have such an edge, one of the potatoes, the entropy decreases substantially. But you could have such a situation, something that looks like a star, and you apply the lemma to these two, but only on this one is the one where the entropy increases. So that's only a small proportion of the potatoes. But using the matching forces it to happen on a constant proportion of the potatoes. So this is a really tiny idea, but it changes the proof. I don't know. I don't know how to